Okay, so we continue our discussion on Kepler's laws. We had, so we discussed about three laws of three Kepler's laws. The first one is okay, so all of these laws are valid for our planetary system. So essentially, k of or rather f of r is equal to minus k by r square. So this is the fourth law for which these three laws are valid. So first law is every planet will have an elliptical orbit with sun at one of its foci. This we have proved. There is no formal proof needed, but because of this particular law of force, it is an obvious conclusion. Second law, it turned out it's a general law for any central force which has a form f r equal to f r r cap. This also we have proved. Now it's time for the third law. Now third law, once again we will see that it is valid only for f r equal to minus k by r square, and it's not a so that is to say it's not an universal law, but it's strictly valid for inverse square force field. So that means gravitation or electrostatic force fields. Now this law essentially says the t is the time period of evaluation in elliptical orbit, and a is the length of the semi-major axis. So in order to prove this law formally, we first have to look into some of the parameters of an elliptical orbit in a more formal manner. Let's do that. We'll just remove this because we need the space. Okay. So this is an ellipse. This is one of the focus. We take our origin here. This is the major axis. This is the minor axis of the ellipse. So this is our center of coordinate system O. Location of any point is given in terms of, location of any point is given in terms of r and theta. So theta is the angle that is made with this particular axis, with between this particular axis and the radial vector. So the equation is L by r equal to 1 plus epsilon cos theta, and it could also be 1 minus epsilon cos theta, because we can just shift the origin from this focus to this focus. We have discussed it already. What is L? L is called semi-latus rectum, and it's the perpendicular that could be drawn through the origin, through the focus, and it will cut these 2 points at, let us say, position P and Q. So length PQ is equal to twice L. It is called the latus rectum. This entire length, the PQ, is called latus rectum. Half of it is OP equal to L equal to semi-latus rectum. Okay. So this is, so we know what is L, what is R, and what is theta. Epsilon, of course, is the eccentricity, and we can show that for epsilon equal to 0, we get a circle. For epsilon less than 1 and greater than 0, that means if epsilon lies between 0 and 1, we get an ellipse. Okay. If epsilon is greater than 1, or sorry, epsilon is equal to 1, we get a parabola, and epsilon greater than 1, we get a hyperbola. Right. This we have not discussed earlier, but this is the scenario. So, for an ellipse, the equation is L equal to R. Sorry, for a circle, the equation is L equal to R, and this is a familiar equation of R equal to constant for a circle. For ellipse, it will be some number, epsilon should be some number between 1 and 0 with this general form. For parabola, epsilon equal to 1. So, the equation is L by R equal to 1 plus cos theta. Similarly, epsilon greater than 1, this equation gives a hyperbola. Now, so we are right now, for in order to prove Kepler's third law, we are more interested in ellipse, because we are talking about closed orbit, and we will see later that this epsilon equal to 0 means a certain value of energy which will give you a circular orbit. That will come later. Right now, we are talking about elliptical orbit, this general equation with this condition on epsilon, and we know that this length is L, this length is 2L. Also, now we have to define two parameters A and B. Okay. Let us try to do that. This is the major axis 2A. So, half of this is A, that is the minor axis 2B, and half of this is B. Now, if the position of this point P is r theta, when we have the origin at this focus, and if we shift the origin at this particular focus, we have a coordinate which is given by P r prime theta prime. So, this will be your r prime and this will be your theta prime. So, what I am trying to tell you that if we have, once we have the origin here, which will give you a position vector r theta, and then we move the origin to here, and this will correspond to a, for the same point it will correspond to a coordinate r prime theta prime. Then it can very easily be shown that, so we will just move it here, this is the condition. Okay. Now, if please consider this point P to be here. Let us say this is the point, we give it a name maybe, I do not know, let us call this Q, let us call this A, B, this point remains O. Okay. So, these are the points we need essentially. So, when the P vector, P point coincides with Q point. So, what happens then? What is R? R is this length, and what is R prime? R prime is this length. Now, this length and this length is equal because the focus is symmetrically placed. So, if these 2 points coincide, we can say that at Q, R plus R prime is equal to twice A. Think of it, R prime, when this point moves here, R prime will be, okay, we will also need a name for this, PQRS. So, R prime will be SQ and R will be OQ, which will be equal to, we will also need a name for this point, SR, yeah, SR. So, this will be equal to this. So, essentially R plus R prime equal to 2A. Now, it can be shown that for an elliptical orbit, anywhere for any point, any point P, any arbitrary point P, this is a valid relation. This can be formally shown, but that is not terribly important. We just, you can take my word for it. So, R plus R prime is equal to 2A at any point. Now, if we now move to another point, just bear with me a bit more because it's a little complicated geometry involved here, so we have to be very precise about it. Now, let us consider this point. So, as I said, this relation is valid not only for this point Q, but it is a general relation for any point. Any point on this elliptical circle, elliptical path, this is the general relation. So, for this point B, this is also generally true. Now, for this point R is equal to, or rather this is R and this is R prime, and we can see from the symmetry of the problem that R is equal to R prime, right. So, OB plus SB, which is once again OB and SB, these two are equal length, we can write it as 2OB equal to 2A. Okay. So, that essentially tells us that OB is equal to A. So, this length will just, we have just proved that this length is A. Now, why I am doing this? Why I am doing this? You have to bear with me for a little longer, then you will know immediately. Now, this length, now this length segment OA, AO, okay. So, AO is equal to AQ minus OQ, AQ minus OQ, right. AQ is nothing but this length, which is once again equal to A. So, we replace it with A. And what is OQ? OQ is, in this relation, if we put theta equal to 0, we get, then our corresponding R is our OQ. So, from this relation we can calculate OQ is equal to L by 1 plus, putting theta equal to 0 only simply gives 1 plus epsilon, right. So, this is 1 plus epsilon, and now if we repeat the same procedure for OR, then please understand that if we put theta equal to 180 here, if we get theta, put theta equal to 180 with respect to this origin, R will move to this point. So, OR is equal to L by 1 minus epsilon. Now, OQ plus OR is equal to QR, which is equal to 2A, which is a summation of these two. So, OQ plus OR is equal to 2A equal to L by 1 plus epsilon plus L by 1 minus epsilon, which on simplification gives you L by 1 minus epsilon square, or there will be a factor of 2 here. So, 2A is equal to 2L by 1 minus epsilon square. So, immediately we see that A is equal to L by 1 minus epsilon square. Okay. Now, we have a expression for OQ, and OQ is L times 1 plus epsilon, with, now if we substitute the value of L in terms of A here, we immediately get L is equal to A times 1 minus epsilon square divided by 1 plus epsilon, which will be nothing more than 1 minus epsilon into 1 plus epsilon, and it will be divided by that. So, it will be 1 minus epsilon, right. So, we see that OQ is equal to A times 1 minus epsilon. I hope it is clear. Now, we go back to this relation and we see A into minus A 1 minus epsilon, which will be simply equal to A epsilon. So, OA is, or AO is equal to A times epsilon, right. So, this length is A, this length is A epsilon. So, finding this length AB is easy, right? That will be simply, okay, so I do not need this part anymore, I just used the calculations we need. So, AB equal to root over a square minus a square epsilon square, which will be a root over 1 minus epsilon square. So, and this AB is what? AB is this length, which is the length of semi major axis. So, which will be B. So, B is equal to 1 by A into 1 minus epsilon square. Right. Now, why do we need all this? We need this because, okay, so we do not use these anymore, we will just keep this safe, because we have to define the time period T. Now, there are many ways of defining time period. The definition we will be adopting is area divided by aerial velocity. This is also a valid definition, because all we need is time it takes to get back to the same point over and over again in this path of oscillation. So, we can use many other definition. Area by aerial velocity is also a valid definition. Now, what is the area of an ellipse? It happened to be given by pi AB, that you know from your geometry lesson. And aerial velocity, we already have derived an expression for aerial velocity, and the expression is L by twice m, L by twice m, which is constant for any central orbit. Right. Now, you see, if I replace this for B, we immediately get pi a square into root over 1 minus epsilon square divided by L by twice m. So, T square is equal to, and we have to rearrange slightly. So, T square equal to 4 m square pi square 4 m square pi square by L square a to the power 4 into 1 minus epsilon square. So, what we can do is, we can use the relation that L is equal to, that we have derived already, L is equal to A times 1 minus epsilon square, right. And so, we can slightly modify this as A cubed into A times root over, or sorry, not no root over anymore, 1 minus epsilon square. Now, this we can simply substitute with L, right, which will leave us 4 m square pi square by L square L A cubed, right. Now, this quantity is a constant, and we can also put the value of L and simplify it slightly, and the final expression what we can do get is essentially T square is equal to 4 pi square m by k, okay, times A cubed. So, this is the term in the bracket can be simplified to this. I am leaving it on you to do it yourself, it is nothing difficult, just have to put the value of L. So, we immediately see a T square, we have proved the Kepler's third law, because this relation tells you that T square is some constant times A cubed, which essentially means T square is proportional to A cubed. So, we formally proved Kepler's third law. This entire mathematical formulation what we did here, the geometrical formulation was needed, so that we can gain an expression, we can write B as A times 1 minus epsilon root over 1 minus epsilon square. Okay. So, hence we have proved three Kepler's laws, starting from very fundamental force law, and now it's time to review different aspect for central orbit. Okay. Okay. So, I am removing this. So, our discussion on Kepler's laws are over. No, I mean not over exactly, we will come back to that, because we can actually apply the third law. We can actually apply the third law, and we can find it is really helpful in order to find the time period of certain orbits. Take an example. Let us say we have Earth here, Moon is evolving around Earth in an elliptical orbit. Once again, it has to be an elliptical orbit, because this is also gravitational force law. Now, we have a artificial satellite, okay, which is evolving around Earth. So, let us call this M and let us call this S. We know that the time period of Moon is roughly 28 days, and Earth to Moon distance from the Earth's surface to Moon, we know the we know the height, we know the distance. So, in principle, we know the semi-major axis for the Moon's orbit. Okay. We also know, let us assume that we also know the orbit of this artificial satellite. So, we know AS. So, if this is the case, we can always write, and please remember that T square is proportional to A cubed, and this is independent of whether it is a satellite or an artificial satellite, it remains the same. This relation, this Kepler's law remains, I mean it holds for both. So, in that case, we can write a relation of the form that T m by T s whole square is equal to A m by A s whole cubed. So, if we know these three parameters, for example, we know this one and this one, then T s square can simply be written as A s by A m whole cubed into T m square. Okay. So, these are the types of application. If we know three parameters in an orbit, the fourth one can be calculated. Okay. Or sorry, rather if we know the semi-major axis of one orbit with time period and semi-major axis of another orbit, then the time period of the second orbit can be calculated. Or also if we know the time period, we can also calculate the length of the orbit, sorry, the semi-major axis of the orbit. Now, this we are not doing right now, because there are some more considerations we need to realize, we need to understand before we can do such applications. So, we are just stopping it here. Before moving out of this particular topic, let me try to solve this problem for you. The problem is problem number 5, up to problem number 4 we have already done. Problem number 5 says a particle P has two constant velocities u and v such that u is always parallel to a fixed direction OX and v is always perpendicular to the radius vector OP. So, a particle P is moving under the influence of some force. We are not sure what is the exact nature of the force, but it has two velocity components which are very defined. The velocity u is always parallel to this OX axis. Okay. So, that we can take this OX axis as a reference axis and we can define this theta angle from there. Now, if we come to the board and draw this over here. So, this is my theta angle. So, once again this is theta, this is V. this is sorry. So, this is u here, and this is v. So, the question says first we have to write down the velocity expression in terms of Vr and v theta. Now, what is Vr? Vr is the radial velocity for this particular point P. It points in this direction. So, Vr will be, of course, V the okay. So, please do not get confused. U and V are two numbers. So, probably I will call it something else. I will call it okay, let us call it Vr. I think you will understand. So, Vr is the radial velocity. So, this v velocity will have no component along this velocity, I mean along the radial direction, because this angle is 90 degree. So, a vector cannot have a component at 90 degree separation. So, that is why v is ruled out. So, Vr will be simply u cos theta. V theta, obviously it is v, and r and theta. So, if this is the direction of r, which one will be the direction of theta? Sorry, if this is the direction of r cap, then what will be the direction of theta cap? This or this? The standard convention is we go in the anti-clockwise direction. So, if this is r cap, this is our theta cap, not this one. This is minus theta cap, right? So, if this is my direction of r cap, my theta cap direction is this. So, this one will have a velocity component which is opposite to this direction. So, v theta can be written as v minus u sin theta, right. So, we could write down the velocity components. Second question is, so this is the part 1. Part 2 of the problem is we have to set up the equation of motion. Please remember, Vr is equal to r dot is equal to drdt, and v theta is equal to r d theta dt. So, if we simply divide one by the other, then we have Vr by v theta is equal to dr by 1 over r drt theta, which will be, from this we get u cos theta v minus u sin theta, right. So, this is my differential equation of motion. We just get rid of this one. This is my differential equation of motion. So, part 2 is done. Now, the third part and the last part, we have to show that the equation of the trajectory of this particle is represented, I mean it is a conic section. So, we have to essentially solve this equation, integrate this equation and bring it to the familiar form of L by R equal to 1 minus or 1 plus epsilon cos theta. Let us see if we can do that. Should not be a problem, it is a simple. So, see that all the theta dependence is on the right hand side. So, we can simply write dr by r is equal to integration u cos theta equal to v minus u sin theta. So, if you take u sin theta equal to some p, so your right hand side becomes there is a d theta here. So, sin okay. So, it will be dp by v minus p, right. So, left hand side, so if we perform the integration, it is ln r is equal to ln v minus p, there will be a minus sign coming, plus we have to add a constant here. So, we just take as ln c. So, ln c by v minus, we substitute the p value of p again. So, it is u sin theta. Okay. So, ln r is equal to ln c by v minus u sin theta. So, if we simplify, we immediately get r is equal to c minus v minus u sin theta, or c by r is equal to u v by u minus 1 minus cos 90 minus theta, okay, or L by R is equal to, oh sorry, it has to be V, sorry, not U, not U. So, if we take V out, it will be 1 minus U by V, right. So, we see L by R is equal to 1 minus epsilon cos 90 minus theta, with L is equal to C by V, epsilon is equal to U by V. Okay. So, we could bring it down to the familiar form. Please recall that plus or minus, it is does not matter, both represents a conic section. We have a reference. So, it is of the form of theta minus theta 0, because it is cos theta, we can write this also as theta minus 90, because cos of minus theta is equal to cos theta. So, we get the general familiar form of L by R equal to 1 minus epsilon cos theta minus theta 0, theta 0 90, L is equal to C by V, epsilon equal to U by V. Good. So, that is it for now, and to the next class onwards, what we are going to do is, we are going to look into the different cases which will give rise to in terms of energy, which will give rise to different types of trajectory. Also, we have to formally see why a two body problem is sometimes not necessarily has to be considered in order to derive the motion under central force. Considering one particle fixed, the force center fixed will also work, that we will see in the next class.